Okay, good evening, good afternoon, good morning, everybody. Welcome to today's ISGC seminar talk. It's my pleasure to introduce to you Chen from the Kagra Institute of Astronomy and Astrophysics in the Department of Astronomy at Peking University. He did his PhD also at Peking University in 2010, and he became an associate professor at the place where he is right now in 2000, as assistant professor, I'm sorry, at the same place in 2016. And since 2023, he is an associate professor. And I will talk with him. When you have questions, please ask him freely during the talk. If you prefer, you can also drop them in the chat. I will monitor the chat. And with that, I hand over to you. Thank you very much for giving this talk. The stage is yours.
Yeah, thank you, Torben. Hello, everyone. My name is Chen Xian. I'm from Peking University. First, thank Torben and also the other organizers for inviting me to give this seminar. It is really my great pleasure to give this talk to such a diverse audience. Torben, by the way, you guys can see my cursor, right? Because I do want to point here and there during my talk. So to make sure you are seeing at the same place that I'm seeing.
Yes, we can see it.
Okay, good. So the title is Distortion of Gravitational Wave Signals by Astrophysical Environments. Go down. I think I will cover mainly a three-part. First of all, I will briefly introduce to you what gravitational wave astronomy is. I think many of you already know what it is. What are the new sciences that it is bringing? I will focus on the challenges that are posed by the so-called astrophysical environments. In a minute, I will explain what I mean by these environments and what are the challenges. Toward the end, I will say something about possible solutions to overcome these challenges. Okay. This is a slide that we all know by heart. This is a gravitational wave. You linearize a field equation, you get the gravitational wave here. I want to emphasize that if you look at the coefficient on the right-hand side of the equation, you will immediately realize that this coefficient is very small. In the CGS unit, the gravitational constant is 10 to the minus 8, and the C is 10 to the 10, but it's to the 4th power. So it's a very, very small coefficient. What it actually means is that gravitational wave couples with matter very, very weakly. Okay, this is why gravitational wave is very difficult to detect. That's also the reason why Einstein, when he first formulated this equation and the gravitational wave, he himself didn't believe that people will one day detect gravitational waves. But the weakness of the coupling is also an advantage, has been put forward by Kip Thorne in the 1990s. Because the coupling is weak, so you can use gravitational wave to probe deep into places where you do not necessarily see with traditional electromagnetic waves. For example, you can see through the cores of supernova, and you can see what is going on in such a dense place, the interior of a neutron star, for example. You can also use the gravitational wave to see places far, far away, for example, to peek into the early universe. We are talking about a redshift of higher than 20, just because lights will be absorbed along its way, because there's a lot of intergalactic medium along the way. But the gravitational wave is almost everything is transparent to gravitational wave. Okay. And you also see, because it's a sort of a dynamical equation, you also see basically the motion of space and time tangling with matter. You see how, say, neutron stars, black hole form with gravitational wave. So these are the things that you don't necessarily see with conventional electromagnetic astronomy observations. That's why we want to detect a gravitational wave. Of course, you all know the story in 2015, September the 14th, the first event detected by the ground-based interferometer was detected. Okay, it's coming from a merging binary black hole. Despite of the significance of this historical event, the best name people could come up with is GW150914. Okay, very plain, dull name. Okay, before we go into a bit detail what actually people are seeing, let me just show you what we understand about stellar mass black holes, because I just told you the first GW event is coming from a merger of binary black hole. This is what we know in the Milky Way through the observation of so-called X-ray binaries. And using X-ray, we know there are stellar mass black holes, the remnants of the evolution of massive stars. They exist in the Milky Way, and these are their masses, okay? The horizontal axis does not have any physical meaning, it's just to place these dots, but the vertical shows their masses. If you have a sharp eyes, you will see that, okay, looks like below 5 solar masses, there's really nothing, no black holes. Above 20, there's no black hole over there. Not everyone agree, but many people suspect that this is actually, there's physical reason behind it. Stars have to be massive enough to form black holes. That's why relatively small black holes is difficult to form. They will go supernova, and then not actually a lot of mass will be lost during the supernova phase. So they become neutron star, not black holes. And above 20, their process is like stability supernova blown up the entire massive star. So if star goes too massive, it doesn't leave you a black hole. So anyway, there's a reason that we only see black holes in between this range from 5 to 20 solar masses. Okay, that was the understanding before 2015, the first gravitational wave event was detected. Then comes gravitational wave detection. Okay, this is the current view of stellar mass black holes and in the universe. To direct you, these red things are the X-ray binaries we were talking about before. And these blue things are the mergers of binary black holes. You see 2 of the black holes merge into 1, detected by gravitational waves, right? You have seen this picture a couple of times. What's important here is that first, you see now there are more gravitational wave black holes than electromagnetic black holes, okay? So this field is really exploding these years. And the second thing you notice that there are a lot of gravitational wave black holes even before the merger. Their masses are already way above 20 solar masses. Some of them even reach 100 solar masses before the merger. Okay, this is a mass range where we have never seen stellar black holes in the Milky Way, never before. So why are gravitational wave black holes so massive? To me, this is one of the most important questions we have to address in the era of gravitational wave astronomy. Of course, there are reasons. In the conventional way for binary stellar mass black hole formation, there's one channel which is a major channel for such things to form. It's called a binary star evolution. Okay, 2 massive stars gravitationally bound as a binary, and they go successfully into a supernova and become, say, black holes. And through the evolution, there's a phase where, say, a common gas envelope can shed angular momentum and energy of the binary. So when the 2 black holes finally form, they're already close enough. Gravitational wave radiation is strong enough, so they can merge within a Hubble time and forming a successful gravitational wave event, LIGO Virgo source, also Kagra source. Okay. In order to form a massive black hole before the merger, you probably need the star to have very low metallicity, so that the stellar wind is relatively weak, less mass is shed during the evolution of the massive star. Most of the mass can go into the black hole. So this is how you produce massive black hole by the end. Okay, there are also a variation of such model. Basically, or they are trying to form first massive black holes, and when the black holes form, try to let the separation of these 2 bodies to be close enough so they can merge successfully within Hubble time. So this channel is called the binary star evolution channel. There's also a so-called dynamical channel. So we also know there are a lot of star clusters. Star clusters is a place where you have a lot of stars that are so dense that very frequently several bodies, more than 2, maybe 3 or 4, or even more, including black holes, will come close to each other and then interact. The outcome of such an interaction is that the massive bodies, say black holes, are preferentially stayed in the same system, and the lighter objects are ejected. So binary black holes could form in this case, okay, because they are the most massive things. They will stay in a binary. And these binary black holes, after they form, they are continuing interacting with the surrounding stars, giving away their energy and angular momentum. Orbital shrinks, and then they could enter the gravitational radiation region, and they could also merge within a Hubble time and become successful LIGO, Virgo, Kagra events. This is the channel for dynamically forming binary black holes. The benefit of this channel is that after the merger of the two black holes, okay, there's a chance that they can stay in the cluster and they may participate in the next generation of binary black hole formation and next generation of merger. So by these successive mergers, their mass can grow successfully to, say, 30, 40 solar masses or even 100 solar masses. So this is certainly another promising channel to form very massive binary black holes. Okay, these are the two major channels for binary black hole formation, at least well perceived before 2015, 2016, before the GW events were announced. Okay, there are other channels I will mention later. But when my collaborators and I saw the results, a lot of massive gravitational wave black holes, the question we were asking ourselves were a bit different. And these different questions basically led us down to a very different path. The question we were asking ourselves is, how is mass measured? Okay, in the end, mass is not a direct observable. What you see is this wavy signal, okay? And in the frequency and time domain, you see there's a signal with time, the frequency increases. These are signals. From these signals, observables you can extract are amplitude, frequency. This is a wave, right? There's an addition, there's a time derivative of frequency, how frequency changes with time, because it's a chirp signal, okay? This frequency increases with time. This is called a chirping. So from these observables, you are trying to infer physical parameters, such as the mass of the black holes and the separation, okay? You see, you need a model to do this inference. So this is not a model-independent business if you want to derive mass of a gravitational wave source. What is a model? So in the simplest case, say binaries are almost circularized. There are reasons to believe that black holes, by the time of merger, they are almost circular. Then you can do this very clever combination of frequency and a frequency dot, get rid of the dependence of the separation, and you get a mass scale. And this mass, as you can see, is a mixture of the two masses of black holes, and this is called the chirp mass. And this chirp mass uniquely determines how the frequency increases with time. There's a third observable that you haven't used yet. This is the amplitude. You can use amplitude to infer the distance, because the further away the source is, the weaker the signal is, right? Because you use amplitude to infer the distance of the object. This is a kind of, you use sound to infer the closeness or distance of the object. So that's why we call gravitational wave sources, especially emergent binary black holes, standard sirens. You can use it to infer the distance using this equation. Okay. This is a very simple model. The universe is actually a bit more sophisticated than that, because the universe is expanding. So there's this redshift. What redshift does to the signal is that it decreases your frequency. It's a redshift. Frequency dot is redshifted even more because of additional time dilation effect. Now your observables are different, right? If you only can get these observables and you want to infer the physical parameters, what kind of parameter you will be able to infer using only observables? It's no longer the real chirp mass. Actually, it's bigger than a chirp mass by the redshift factor. Here is a cosmological redshift factor. Unless you can independently measure this redshift factor, otherwise, what you directly get from the signal is always a bigger mass. You always overestimate your mass. Okay, this is a point. And this degeneracy is called mass and redshift degeneracy. It was already known in the 1980s. I think Bernard Schulz probably formulated it in one of his papers. actually, you also overestimate the distance. Okay, if you use only observables, combine them to get a distance, you will see that the apparent distance is bigger than the co-moving distance, also by this redshift factor. But in standard cosmology, this product here is the luminosity distance. Okay, so that's why people say using standard sirens, you measure luminosity distance. Okay, right. So if redshift exists, you always overestimate the masses of black holes. Why do people believe that the black hole we detect with gravitational waves are indeed very massive? The reason is the following. Okay, so this is the first detection, GW150914. I already told you how to derive the apparent mass and the apparent distance. The apparent distance is the luminosity distance, right? If there's only cosmological redshift. So using the apparent distance, you assume a standard cosmology, lambda CDM, for example. You can infer that the redshift is 0.1. The redshift factor, 1 plus z, is 1.1. It's very close to unity. It's not a very big number. So the real mass is smaller than the apparent mass by only a factor of 1.1. It's not a big deal. That's why people believe what we actually detect is really massive black holes. However, my background is in astronomy. So besides cosmological redshift, I know at least two other redshifts, Doppler redshift and gravitational redshift. If a source is moving very fast away from you, there will be a Doppler redshift. If the source is in a very deep potential, okay, then there will be gravitational redshift. If redshift always boosts the apparent mass, make you overestimate the mass of the source, why haven't the people seriously considered the latter two redshifts? They only consider cosmological redshift. Why? So this was the question my friend Shuo Li, now at National Observatory of China, and also Cao Zhoujian, now at the Beijing Normal University, were asking ourselves back in 2017 when I just came back from abroad. There's a reason. I told you what's the conventional formation channels for binary black holes. They form in galactic disks, bulges, globular clusters, etc. So the velocities of these sources are not very large. Okay, so people think, okay, the Doppler shift is negligible. The potential is not very deep either. That's why people think gravitational redshift is not important either. However, this view, which is based on the conventional formation channels, I think now we can at least safely say is incomplete. Over the past 7-8 years, okay, many people, including my group, start to realize that in the centers of galaxies, especially close to supermassive black holes, you might have an enhancement of the formation and also the merger of binary black holes. I'm borrowing a sketch from Hiromichi Tagawa. He is also now working in China in Shanghai Observatory. The reasons are multifold, okay? Close to the center of galaxies, close to supermassive black holes, escape velocity is very large, so compact objects can preferentially stay there. There's naturally a high density of compact objects. And there's also an effect called mass aggregation, which will lead massive objects like black holes, neutron stars, to go even deeper into the bottom of the potential well. So the concentration of compact objects there will be even higher because of this dynamical effect. Then the chance of forming binary is high. After the binary black hole form, they will interact not only with the surrounding massive object, but can also interact with a nearby supermassive black hole. So tidal force is quite large, and which can sometimes can disrupt the binary, but in other cases can excite the eccentricity, and then eccentricity is helpful for the merger of the binary. So this is actually a way of boost the merger rate of binary black holes close to supermassive black holes. And there's also a very special system called active galactic nucleus, AGN, like quasars, for example. They have accretion disk around the supermassive black holes, and the binary black holes, by interacting with the gas in these accretion disks, can more easily give away the energy and angular momentum in the orbit, and then they will more easily merge. Okay, all these factors combined lead to the result that close to supermassive black holes, merger rate of binary black holes will be high. Okay, now it's actually possible because of this reasoning that binary black hole can merge very close to a supermassive black hole. Then the velocity of the source is very large because it has to move very fast in order not to fall into the supermassive black hole. Then Doppler shift start to be important. Gravitational potential close to supermassive black hole, of course, is very deep. Then gravitational redshift has to be taken into account, okay? So then it will be very interesting. What if a binary black hole merges very close to a supermassive black hole? Then it's without a very difficult calculation, you can do it by yourself. It's easy to verify that, okay, besides cosmological redshift, you have to take Doppler and the gravitational redshift into account. It will boost your measurement of the mass as well as the distance by even a much bigger factor. This is an early version of the calculation, and later we just discovered that here, especially for the distance, there will be another factor. So it's proportional to the Doppler redshift by square. Okay, there's another redshift factor here, but that doesn't matter. The point is that the measured apparent mass and distance actually will be even bigger if these two redshift become important. I can give you an example. You can put a binary. This red dot now represents a merging binary stellar black hole. Okay, you can put it around a supermassive black hole. Let's, for simplicity, assume circular orbits. Okay, what is the smallest distance you can put this binary relative to the supermassive black hole? We all know that if the central supermassive black hole is not spinning, it's a Schwarzschild black hole, then it's the innermost stable circular orbit, 3 Schwarzschild radii. The velocity on this orbit is 0.4 c, okay, a significant fraction of the speed of light. You can imagine Doppler shift will be very important. Gravitational redshift is also very important. And then if you combine these factors and calculate it, it of course depends on the viewing angle of the system. This redshift factor in this red box can be as large as 1.9, almost a factor of 2. This is already a very, very interesting factor because a normal, say, 15 solar mass, 20 solar mass black hole after this redshift will look like 30 to 40 solar masses. 30 to 40 solar masses are the typical black holes we see with gravitational waves. Okay, so it's becoming interesting. Okay, then more interestingly, if the central supermassive black hole start to spin, it's a curved black hole, then you have to do more serious calculations. So I asked a former student of mine, Xiaoyue Zhang, to do this calculation. We put a binary close to a central curved supermassive black hole. The binary is put at a very small distance, circular orbits. Okay, I think it's a 6m. Okay, 6 gravitational radii. You will see that when the gravitational waves are just emitted, they can be blue or red shifted depending on the direction of emission of the gravitational wave relative to the orbital velocity. Okay, but all these waves, after they come out of the source, have to climb out of the very deep potential. So in the end, the gravitational redshift will start to take effect. Okay, it will predominate. So when these waves propagate to further and further away, you will see that they all become kind of red. So the gravitational redshift will take over. Another thing you notice is that, okay, there are places where these rays start to diverge. This indicates that if you are seeing the source in this direction, the source will be demagnified, okay? And you will see a weaker signal. This will affect your inference of the distance, okay? There are also places actually where the rays start to converge. In these places, not necessarily here, but in other places, the signal will be magnified. And this will also change the apparent amplitude of the source, and this will sort of mess up the inference of the distance of this source. Okay, this is kind of a gravitational lensing effect in the strong gravity region. Okay, so when you combine all these effects, blue, redshift, and gravitational lensing, and you ask, okay, if I detect a signal and I try to infer the mass and distance, what would the results be? And this is the result. This is what you would infer for the mass and the redshift. Okay, you think it's at this cosmological redshift. Okay, the redshift of this emergent small binary. Let me tell you where the real source is. Here we put very normal, regular 10 solar mass plus 10 solar mass, a binary black hole, close to a supermassive black hole, supermassive curve black hole, okay? The distance between the binary stellar mass black hole and the supermassive black hole is very small, 3 m. And the whole system, it's actually a 3-body system, is placed at a real cosmological redshift of 0.1, 400 megaparsec. So this is a real location of the source. But because of the effect I told you here, if you look at the source at different angles, these are red and the black dots are just the images of your signal. You see some images, if you use standard gravitational wave template to fit the mass, you will overestimate the mass. This is exactly because of the redshift effect I told you about in the last few slides. There are also places you can underestimate the mass. This is because in some directions, the rays are really blue shifted. So the trend is kind of in the opposite direction. You underestimate the mass if blue shift is important, okay? But redshift predominates because, like I told you, gravitational redshift is important for most of these directions. There are also these very, very interesting images, although they are very rare. They do not happen quite frequently, but they're there. They look like what? They look like subsolar mass, smaller than 1 solar mass, black holes, merging at extremely high redshifts, redshift 100, okay? They look like primordial black holes, but are they primordial black holes? No, they're not. They're just highly demagnified images of such a system. They are demagnified, the signal is extremely weak, so you would infer, using standard template, you would infer that these sources are at extremely high redshift, but they're not, okay? It's just a fake primordial black holes or fake massive black holes because of these effects, okay? And if you want to use these kind of sources to do cosmology and infer distance, what will you get? I'm not sure, but certainly very dangerous. Okay, so I just told you if this thing happened, okay, a binary black hole merging very close to a supermassive. If this happened, then this effect will be important. But this is a very small distance. Here is a 6 m, here is 3 m. They're so close. Is it possible that in the nature such kind of system can form? So this is the next question we were asking ourselves. How can these things form? In order to understand how they form, let me go back one step and tell you normally how you can send stellar black holes to a central supermassive black hole. Okay, supermassive black hole is here. There are different channels. One of the channels is a so-called binary separation channel. If a binary stellar black hole forms far away from the supermassive black hole, but they are scattered by the surrounding stars to the vicinity of supermassive black hole, then the tidal force of the supermassive black hole can separate the binary. One of the members will escape, but the other, because of the conservation of energy, will be gravitationally bound to the black hole. This is how supermassive black holes can capture stellar black holes, form a sort of extreme mass ratio system, or called extreme mass ratio in spiral. The gravitational radiation happens to be in the low frequency millihertz range, so it's suitable for the future space detectors like this laser interferometer space antenna, LISA, or China's Taijian Tianqing, the detector to detect. Okay, this is a good millihertz gravitational wave sources. But you have to send this binary to extreme close distance relative to the supermassive black hole. What if the closest approach, the pericenter, is not so close? Then the binary is not completely separated. It still feels a tidal force. The binary gets kind of heated a little bit. It absorbs energy, okay? The energy comes from the outer orbit around the supermassive black hole, right? So because of the energy goes from the outer orbit into the internal energy of the binary, then the outer orbit had to be lowered. The binary become captured if the pericenter is not so close. This is a mechanism known actually already in the 1990s as a tidal capture. You can capture binaries in this way. Interestingly, in 2015, there were some simulations simulating the interaction between stellar mass binary black holes with a central supermassive black holes. In the simulation, they also find a lot of the binaries get captured. So we look at this Addison et al. Their results and sort of derived this analytical formula to understand after capture, what is the pericenter of the captured orbit? The pericenter, depending on other parameters, of course, is very, very small, 21 gravitational radii. Okay, from here to here, you have a captured binary, and the pericenter is only 10 threshold radii. And we also verified these results by our own version of numerical simulations with Wen Biaohan from Shanghai Observatory. Okay, so these binaries can be captured by supermassive black hole, but we want these binaries also merge. Do they merge? Because we want these binaries to become LIGO Virgo Kagra sources. So this is a simulation simulating the semi-major of this binary, the inner binary, the semi-major of these two bodies, as well as its eccentricity evolve with time. This is plotted 1 minus e. So going down actually means a very, very eccentric binary. 0, oh, sorry, 10 to the 0th order. So 1 is a circular binary. You see that most of the time, the binary does nothing, okay? Semi-major X eccentricity constant. And then there's a glitch. This is because the binary is passing by the pericenter, is strongly interacting with the central supermassive black hole. So there's this glitch, and then does nothing again, and there's another pericenter passage and does nothing again. But after a couple of these interactions, what's interesting is happening here, shown by these dots. If you zoom in, you will see that the semi-major change and the eccentricity go down to very, very small value. Actually, if you look at the E, it's 0.999 something. Suddenly become very, very eccentric because of the excitation of eccentricity by the tidal force from the central supermassive black hole. But then gravitational radiation actually between the two binaries will take over, and the binary will merge here relatively close to the pericenter, because this is where the eccentricity is excited to a high value. So this kind of explains why the merger doesn't happen earlier, but have to wait until the binary is very close to the black hole. Then the binary will merge. Okay, this is kind of interesting. When the binary merges, it's already inside the 10th threshold radii. This is exactly what we need. We need a source to be embedded deeply in the potential well of the central supermassive black hole. And then you can fold in, say, some population, like how many supermassive black holes are there around each supermassive black hole, how many binary stellar black holes are there. This is kind of a dynamic model, and you can try to predict the event rate, how often this kind of event will happen. This is a number. It's not important. What's important that looks like it's still very rare. It only accounts for 0.1% of the LIGO Virgo detection rate. Okay, it cannot account for the majority of the sources. The reason that these events are rare is because the binary cannot be too wide. If it's too wide, it will be tidally disrupted. It cannot be too compact. If too compact, the binary will merge even before it reaches a black hole. So there's a very narrow window that this mechanism will work. This greatly diminishes the event rate. Okay. Oh, okay. Looks like this is not a very promising channel of producing our redshifted sources. But we were not deterred by this, and we decided to go on to study other channels. We know there's another channel of sending binaries to the vicinity of a supermassive black hole. It's an AGN accretion disk channel, like I told you a couple of slides back. For a long time, people know that in AGNs, supermassive black hole is surrounded by accretion disk. There's a lot of gas in it, and then stars, especially massive stars, can form in it. And these massive stars will go supernova and become compact objects like stellar mass black hole neutron stars. The disk is also capable of capturing some black holes and neutron stars in it. And these black holes and neutron stars in the disk will interact with the gas, migrate inward and outward. Then they will catch each other, form these binary stellar black holes, binary neutron stars, black hole neutron star binaries. After their formation, they will continue interacting with the surrounding gas. Gas is dissipative. It can take away energy from the binary, and the binary can merge very quickly. So this is a way actually to create a lot of LIGO Virgo Kagra binary black hole merger. And this is already relatively well known, even since the 2012. Okay, there's some later follow-ups of this idea. But can these binaries formed in the disk enter a region very, very close to a supermassive black hole? That's the interesting source in our mind, right? In order to understand this, you have to look a bit closer at the structure of accretion disk. Normally, accretion disk is hotter inside, cooler outside, because everything here is moving so fast, it creates more heat. Then you will create a pressure gradient pointing outward. If you look at the direction of pressure gradient, it acting in the same direction of centrifugal force against the gravity. Okay, this equation actually tells you centrifugal force determines the rotational speed of gas in the disk. In such a disk, especially very hot disk, the rotation can be relatively slow. And the pressure can help the gas to stay at some radius, okay? So the gas is rotating slower than the Keplerian velocity. But small black holes, like these small dots here, embedded in the disk, they are small. They do not feel as much pressure. So these black holes, in order to stay here, they have to go around the black hole on Keplerian velocity, on Keplerian orbits. So small black holes actually are moving faster than the surrounding gas. Then effectively, these small black holes, because they're moving faster, they feel kind of a wind from ahead. It's a headwind. Headwind is pushing the small black hole. They feel effective friction, and this friction will lead the orbit to decay, and then these small black holes will gradually migrate toward the central supermassive black hole. And this is already known also a long time ago. If you embed small objects in the accretion disk of AGN, they will migrate inward because of this mechanism. So there's no problem for the binaries or single black holes to migrate inward. Then the question is kind of reversed. Can you stop them at the inner edge of the disk? Because if not, then these stellar black holes will one by one fall into the central supermassive black hole and has no chance of finding another stellar black hole, form a binary, and successfully merge, become like LIGO, Virgo, Kagra sources, right? So you need a mechanism to stop them in the inner edge. Then there's a higher chance for them to form binaries. Is there such a way? Then you have to look even closer around the supermassive black hole. And this is actually the equipotential of the gas, very, very close to the central supermassive black hole. You are seeing this kind of a very special structure because of GR, as well as conservation of angular momentum. Okay, very close to supermassive black hole, especially when the accretion rate is very high. The angular momentum is kind of conserved. It's they fall into the black hole before material can shed away their angular momentum. Okay, then you will have this equipotential. This is where the potential is the deepest. Also, the pressure is the highest, and you go towards the black hole. The potential kind of becomes shallower. Pressure becomes smaller. After you cross this sort of cusp, then the potential deepens again. But in this region, indicated by the blue line, there's a pressure gradient pointing inward. Now in the same direction of gravity against the centrifugal force. This indicates that gas here actually rotates faster than the Keplerian velocity. Then the situation is reversed, right? Then stellar mass black hole reaching this region, their stellar black holes are moving at Keplerian velocity, but gas is moving faster than Keplerian velocity. Then stellar black holes are actually feeling not a headwind anymore, but a tailwind, a wind from the back, pushing the stellar black holes forward. The stellar black holes will gain angular momentum. If they gain angular momentum, they will migrate outward. So they cannot go in. There's a barrier here. This phenomenon actually was already at least theoretically discovered in the 1990s. They find that you put a stellar black hole in, if a little bit further away, it will migrate inward because of the headwind. But if you put a stellar black hole too close to the central supermassive black hole, it will migrate outward because of the tailwind. So all the stellar black holes will kind of converge at some radius. If you look at this radius, this is in unit of Schwarzschild radii, it's very close. Within 10 Schwarzschild radii, very, very close to supermassive black hole. So I asked the student to kind of first repeat this calculation. Yes, indeed. We find that when the accretion rate of the disk is very high, These curves are the sort of the rotation curves of the gas. There's a horizontal line. Below this line is the subcapillarian. Above this line is the supracapillarian. So there is indeed a region, the gas sort of changes from subcapillarian to supracapillarian. And we think this region is where most of the stellar black holes, compact objects in the disk, will accumulate because of the mechanism I just told you here. If a lot of compact objects accumulate here, then they will naturally form binaries and merge. And if you look at where this region is, this is in Schwarzschild radii unit. Okay? They are all clustered inside the 10 Schwarzschild radii, very close to supermassive black hole. Great, they could be highly redshifted. Okay, so do these traps really exist for all kind of black holes, all kind of AGN? Then you have to do kind of a parameter survey. So this axis is the mass of the central supermassive black hole. To guide your eye, this is 10 to the 8th solar mass supermassive black hole. Okay, this is the mass of the compact object or the binary stellar mass black hole. If you are thinking of the 20 solar mass black hole, it's about here. Okay, in a large region of the parameter space, you don't have this trap because migration is too fast. As soon as a binary or single stellar black hole reach this region, they will be flushed into the central supermassive black hole. But there is a region in this parameter space where you do have this trap. Okay, these numbers here show exactly where the trap is in the Schwarzschild radii unit. Okay, you see they are all smaller than 10 Schwarzschild radii, so extremely close. Because further inside, there's no more such traps, so we kind of call it the last migration traps for compact objects in the accretion disk. And then you can fold in a kind of a population model and you try to predict the event rate, like you count how many quasars you will have because you read high accretion rate. Quasars happen to have high accretion rate, and you have a model for how many stellar black holes are there in each quasar disk, etc. And you can get this number. Important thing is that it only accounts for 2% of all the reported LIGO Virgo detection. Again, okay, looks like it cannot explain all the massive gravitational wave binary black holes. It might seem to you a very small fraction, but don't forget that LIGO Virgo so far, after 3 runs, have already detected almost 100 binary black hole mergers. We know there's a force observing run going on, and already there are about 80-something binary black holes reported. And this number, almost 200 times 2%, okay, some of them probably are coming from this channel, right? Interestingly, in the first 3 runs, there was this GW190521, okay, discovered in 2019. This is one of the most massive binary black hole merger reported so far by LIGO Virgo collaboration and the Kagra collaboration. Okay, the mass before the merger already reached almost 100. Okay, what's interesting that in the same sky area, after 1 month actually after the gravitational wave event, which is indicated by this line, there's an AGN flared up in the same sky area. Okay, this is showing you the G band, R band. This is the optical bands. There's a flare. So because of this flare, people, some people like Graham, etc., suggest that okay, this AGN flare is associated with the GW190521 event. But now you have 2 ways of estimating the distance. One is from gravitational wave signal alone. I told you how to estimate the gravitational wave distance, right? So from the signal, it looks like the distance is 4.5 gigaparsec, okay, by just analyzing gravitational wave data. Because we see an AGN, we detect actually the broad line and narrow lines, and we can identify the host galaxy. So the host galaxy has a redshift. Using the redshift, it seems that the AGN is located at a distance of 2.2 gigaparsec. So this electromagnetic distance does not match the gravitational wave distance. And this inconsistency for many people is a reason to reject the suggestion that this AGN is associated with a gravitational wave source. So many people think this is a coincidence, not physically related. But this difference a factor of 2 difference, right? It's kind of expected in our model. If the source is redshifted by a factor of 2 because of Doppler and the gravitational redshift, the source is experiencing because the source is very close to a supermassive black hole. So we kind of think this is interesting, and this factor of 2 is also very interesting. In order to have this redshift, the binary merge is already around the innermost edge of the accretion disk, but not quite the ISGO yet. Okay, so the binary is also at a very interesting location, if our model is correct. And a couple of years back, Graham updated their search and find a couple of more candidates. I think it's interesting to look into. Okay, let's just take a brief break and think of what we have talked about so far. So what we are talking about is this system. You have a binary stellar mass black hole for some reason, getting captured by the central supermassive black hole, and its binary is orbiting around the supermassive black hole. This is very similar to the extreme mass ratio kind of system, but different from the standard Emery, standard extreme mass ratio spiral. The small body is not a single black hole. The small body is a binary. So my collaborators and I call it binary Emery or B Emery. This small b stands for small binary. The interesting thing about this B Emery system is that when this binary stellar mass black hole merges, it produces high frequency gravitational wave, which is detectable by the ground-based detectors like LIGO, Virgo, and also Kagra. But its orbit around the supermassive black hole is at the same time emitting low-frequency gravitational waves in the millihertz, which is detectable by the future space-based detectors like LISA. Okay, so the source is simultaneously producing both high and low-frequency gravitation. It's very interesting. If you detect it, it's like listening to a duet of a remarkable source in the universe. Okay, so that's why we think kind of interesting. How can we distinguish such gravitational wave events from the rest normal binary black hole mergers, right? So far, LIGO Virgo, after 3 observing rounds, reported about 100, and in 04, there may be another 80 binary black hole mergers. Which one of them, or what fraction of them actually are coming from this BMR system? How to distinguish them? Using LIGO, Virgo, also Kagra alone, it's very difficult to distinguish because you only see the signal for the last 0.1 second. Before 0.1 second, before the merger, it's pure noise. Okay. During this 0.1 second, how long the source has moved, you time the velocity of the source. The source is close to a supermassive black hole. Velocity is a large fraction of the speed of light. Okay, this is several thousand kilometers. Compared to the curvature radius of the central supermassive black hole, the distance that the source has traversed during this 0.1 second is negligible. So the source, for all purposes of observation, stays in the same location. Okay, so the redshift doesn't change with time, and then there's the mass and the redshift degeneracy. So there's no way you can distinguish whether or not this source is redshifted or not, by whether there's a nearby supermassive black hole. It's difficult. But with next generation ground-based detectors like LIGO Plus or Cosmic Explorer, we will be able to follow the source for more than 1 second because the sensitivity is very good, so the noise level is very low, or even maybe 10, 100 seconds. Then you start to see the source moving a distance about 10 to the 5 or 1 million kilometers. And this distance becomes comparable to the curvature radius around the supermassive black hole, which is several million solar masses, a black hole, which we were talking about. Okay. And then you start to see the motion. And then there's a chance that you will see a change of the redshift, and then you will be able to probably tell the difference with the next generation ground-based detectors. With LISA, because LISA detects really low frequency waves, it can already capture or catch these sources even a year before the final merger in the LIGO Virgo band, right? So during this year, you can track this source, then the motion of the source around the supermassive black hole is very obvious. and the LISA band, like our colleague Koki Inayoshi here proposed. There are several similar works around the same year. Okay, so you will be able to see the motion of the source around the supermassive black hole. But now, when you can catch the source relatively long before the merger, the signal is very long. You come into another problem. The signal is so long. Is your model actually accurate enough for you to generate a very accurate template? Because even if a small error in your model, then you match the first few cycles of the signal, the later few cycles, there's a big deface. You lose the later part of the signal. You will lose signal to noise ratio if your model is even a little bit inaccurate. Okay. Then even if the source is there in the LISA data stream, you will not be able to dig it out because you do not have a good template. Then you ask, okay, our model, are they sufficient to simulate such a system, which is a three-body system for such a long time, several years? The conventional tools will certainly fail. For example, if you lose the normally used method to simulate three-body system is post-Newtonian formalism with some GR corrections, of course. This will fail because the post-Newtonian formalism assumes low velocity. Here, the source is moving very fast around the supermassive black hole. Full numerical relativity, solve Einstein's field equation directly, will also fail because you not only have to resolve the motion of this small binary. It's a very, very small binary. You also have to resolve its motion around the bigger black hole. The size of the small binary and its orbit around the big black hole differ by 6 to 7 orders of magnitude. The current numerical relativity tools cannot simulate system with such dynamical range. Okay, so it's impossible. Then what can we do? New methods have to be designed. Well, there's a way. So if you think about if you are a free-fall observer falling together with a binary around a supermassive black hole, then in this free-fall observer's frame, the dynamic evolution of the binary becomes very simple because gravity from the central supermassive disappears. This by equivalence principle. The binary in this frame only evolves according to the mutual gravity between these two small bodies. This is relatively weakly relativistic, so it's very simple to solve. It's almost Keplerian in the free-fall frame of this observer. Okay, but the binary in the end is not placed in a very flat background. It will feel a small curvature induced by the nearby supermassive black hole. So within the region of this small binary, there's a little bit small curvature. So the small curvature produces some perturbation. One is kind of effectively a tidal force to move the object from its original region. The other is kind of bend its trajectory. When it moves, the velocity will also bend. But these effects are very well understood. It's called the gravito-electromagnetic forces because it looks like there's the electric field acting on this mass charge, and there's a magnetic field cause a trajectory to bend. This is by an analogy between gravity and electromagnetism. Okay, it's not like there's a yes.
You're approaching 55 minutes, so
yes, I'm going to finish in maybe a couple of minutes.
Okay, thanks.
So these small perturbations can be introduced in the free-fall frame, and so I asked the student Zhongfu to do this calculation, and this is basically what you see. So in this free-fall frame, if there's no electromagnetic force, then the two binary will do concentric circle. But exactly because of these gravito-electromagnetic forces, you see the circle sort of drifts. And this is kind of new phenomenon that has not been reported before using conventional methods. And what's important is that if you place the binary very close to the supermassive black hole, you see the eccentricity also start to oscillate. When eccentricity is high, the binary will merge. Here we are placing the binary at 2.8 gravitational radii. This is also an interesting coincidence. The binary doesn't merge earlier, but has to wait until it's very close to the central supermassive black hole to merge. This will produce a highly redshifted source as we are expecting. Okay, this slide I just want to show if you go into the literature a little bit, you will see that this is not a new idea. This idea can even date back to Weber in the 1960s. Okay, I don't have time to go through this, but if you are interested, we can discuss it later. Evolved around this idea, there are a lot of interesting things. How to use this BM system to test not only astrophysical processes, but also fundamental physics. Okay, this is a summary. I will just say that astrophysical environment is important. If you ignore it, it will normally lead you to a wrong parameter of the source. And with this wrong parameter, you can interpret the origin of black holes very wrongly, and you might even get a very wrong cosmology if you want to use it as standard standard. Okay, that's all. Thank you.
Okay, thank you for the nice talk, Xian. Other questions?
And then the next one.
Sure.
Thank you very much, Chen, for the nice talk. So I have a question, like when you model the effects of environmental effect, in particular, when you consider the merger events near supermassive black hole, supermassive black hole usually has a accretion disk. And so do you have to take into account the gravitational effects of the disk itself? Or like, do you think that if we neglect that the self-gravity effects of the disk, would that give you some wrong interpretation?
Very good question. There's gas around, but when the binary enters the LIGO-Virgo band, okay, the gravitational wave radiation predominates. It's the main channel of taking away energy. The surrounding gas has no comparison. If you consider friction and also the direct gravity between gas and the binary, there's no comparison. Gravitational wave still predominates. So in the LIGO-Virgo band, you can safely ignore the surrounding gas if you are thinking of accretion disk kind of environment. But if the binary is still in the LISA band, the binary is much wider. Emission of gravitational radiation is much weaker. So there's a chance actually here for gas to take over, to dominate the evolution of the binary. There, you have to take into account the effect of gas. For example, the friction of gas will dissipate more energy than gravitational wave. And this is taken into account by us and also by some other groups in the past.
Thank you.
Are there other questions? If not, I would suggest to simply end the official part here and then go to the free discussion. Geo, could you stop the recording?